Hey everyone, we already learned how to do u sub with indefinite integrals, and now we're going to learn how to do it with definite integrals. Alright, so it only adds one extra step. So same process here, I see x squared plus 1 is being cubed, so that's a good candidate for u. Now I take the derivative, and I don't have 2x dx, I just have x dx, so I'm going to divide both sides by 2. Alright, so same process we've done before. The only extra step is now I'm going to plug all this stuff in. I have to change my bounds. Okay, so my bounds were in relationship with x. Okay, so this all was with x. Now my bounds have to be in terms of u. All right, this is a totally different function. Okay, x times x squared plus 1 cubed is totally different from 1/2 u cubed. Okay, now the cool thing is that it'll still give me the same integral. So it'll still give me the same area. I just have to find different bounds that work for this. Okay, so how I'm going to show that is I'm going to say when x equals 1 and then x equals 2, I'm going to find the corresponding u values. And I already have a relationship between u and x. It's right here. All right, so if I plug 1 in, I'll get that 1 squared plus 1 is 2. If I plug 2 in, 2 squared plus 1 is 5. So my new bounds are, instead of 1 and 2, it's 2 to 5. All right, we'll take the integral. And so before, I would substitute u back in at this step. We don't have to do that now. All right, because I changed my values here, my bounds, I can just go ahead and do the fundamental theorem and just plug these in without having to substitute back. All right, and so you could substitute back and not change your bounds, but most of the time that will result in a more complicated calculation at the end. All right, this is fairly simple to do, and so that makes the end product here much easier to handle, I promise. All right, so 1/8, we have 5 to the 4th, and then 2 to the 4th. All right, so that ends up being 609 divided by 8. Okay, so really similar process, So here I'm going to let u be 1 plus 2x squared, take the derivative, and divide both sides by 4. All right, now I'm going to have to change my bounds. So when x equals 0 and x equals 2, when x is 0, u is 1. When x is 2, 2 squared is 4, times 2 is 8, plus 1 is 9. So now I'm going to rewrite this as 1/4, so this 1/4 is going to go here. Integral from 1 to 9, right? And then I have u to the negative 1/2 power with respect to u. All right, so this 1/4 du is right here, 1/4 du. This is u, but it's a denominator and it's a square root, so negative 1/2, and then my bounds change to 1/9. All right, so I'll have 2u to the 1/2 from 1 to 9. It's going to be 1/2. So 2 times 1/4 is 1/2. 9 to the 1/2 minus 1 to the 1/2. That's 3 minus 1. So I have 1/2 times 2. This is 3 minus 1, which is just 1. All right, next example. Of course, we have to do some trig. So I'm going to let u be 3x. That means du is 3 dx. I already know I'm going to have to divide that 3 over, so I'm going to go ahead and do that. Now I have to change my bounds. So when x equals, pi over 12, and then x equals pi over 9, so I'm just going to multiply these by 3. So u will be pi over 4, and u will be pi over 3. So my new integral is 1/3, integral from pi over 4 to pi over 3 of sine of u du. Right, the integral of sine is negative cosine of u from pi over 4 to pi over 3. All right, so we can just plug this in. I'm going to take this negative out. So negative 1/3 cosine of pi over 3 minus cosine of pi over 4. All right, cosine of pi over 3 is 1/2. Cosine of pi over 4 is root 2 over 2. Right, so we'll end up with, these will flip, so I'll have the square root of 2 minus 1 over 6. Alright, let's keep going. Alright, so some more trig. So I see that sine is being cubed, so I'm going to let u equal sine. That means du is cosine dx. Alright, so again, I'm going to change my bounds. So when x is 0 and then x is pi over 6, so sine of 0 is 0, and sine of pi over 6 is 1/2. Right, so my new integral is from 0 to 1/2 u cubed du. Much simpler integral. Much simpler integral. Alright, so I have 1/4 u to the 4th from 0 to 1/2. And so that's going to be 1/4 times 1/2 to the 4th, which is 1 over 64. Right, pretty straightforward. Alright, so now they give us a picture. This function is x times x squared plus 1 from 0 to 2. So I'm looking about here. Alright, I'm trying to find this area. Alright, so I take the integral from 0 to 2 of x squared plus 1 with respect to x. That's how I'm going to set this up. Now I know I'm going to do a u sub, so I'm going to let u equal x squared plus 1. That means du is 2x, and I'm going to bring that 2 over, sorry, dx. So I have x dx over here. And I'm going to change my bounds. So when x is 0 and x is 2, u is going to be 1 and u is going to be 5. Alright, so my new bounds, 1 to 5, I have a 1/2 here, u to the 1/2 power du. Right, and it's pretty cool that this is equivalent to this. So this complicated curve here, now u to the 1/2 power obviously does not look like this at all. Okay, that's more of a square root. And it's being compressed. So it's kind of like that. And then like from 1 to 5, which is way out here, and the area under this square root curve is equivalent to the area under this more parabolic looking curve. Totally crazy. Okay. So I take the integral here, so 1/2, it's going to be 2/3 u to the 3/2 power from 1 to 5. Right, so that means that I have 1/3 times 5 to the 3/2 minus 1 to the 3/2. Right, and we're going to get an ugly answer here. There's no real good way to simplify this. We'll get like 2 square root of 125 minus 2 over 6. Yeah, we could reduce that a little bit, but I'm not going to worry about it too much. So that'd be like 10 root 5 minus 2 over 6. Whatever. Okay. Remember, simplification isn't a huge deal. All right, last example, we're just talking about Riemann sums as approximations of my definite integrals now. Right, so remember, a Riemann sum to infinity, so the limit of a Riemann sum to infinity is going to be my definite integral, but I can also use a Riemann sum to approximate, very similar to when we do average rate of change to approximate instantaneous rate of change. It's a very similar idea here. In this case, the Riemann sum would be like the average rate of change, and the integral will be the instantaneous rate of change. Okay, very similar idea. All right, so I have a table. It's impossible to find the exact integral, but I can approximate it. So I'll do the approximate, big deal there. And I want to do a left Riemann sum. So between 0 and 5, width of 5, the left point is 14. Between 5 and 9, it's 4, the left point is 18. And so on. So 6 and 20, and then 5 and 27. Right? We do the math, we get 397 gallons. Right? Same deal here. I want to do a right Riemann sum this time. So approximate between 0 and 5, my delta x is going to remain the same, but I'm going to use the right point, so this time 18, and then 20, and then 27, and then 32. And remember, I'm not going to use this leftmost point when I do a right Riemann sum. We do the math, we get 492 gallons. Right, and that's it. See you all later.